The fan-out, fan-in pattern paid for itself the week 2 successful runs made one bad ledger. We had parallel agents collecting updates, scoring them, and publishing results. Each writer was confident, each had a clean log. The database was not clean. One run marked an item complete, another reopened it from older evidence, and the audit trail looked like a debate with no moderator. Nobody corrupted it by reading. The damage happened when 2 nodes held the pen. That failure is why I treat single-writer fan-in as failure isolation, not neat architecture. Naive agent graphs often copy the human team chart. 5 workers, 5 tool calls, 5 chances to update the shared artifact. That feels fast, and for reading it usually is. 5 researchers can open pages, query APIs, summarize documents, and score candidates without damaging the system, assuming their tools are read-only. But writing is different. Writing changes durable state, a ledger row, a file, a ticket, a customer record, a deployment plan. Parallel writers create race conditions with confidence. Worse, each writer explains its own action locally, so blame is distributed across logs. You get speed, but lose a single place to verify intent before state changes. The pattern is simple. Fan out the reads, fan in the writes. Send N researchers to collect evidence in parallel. Let them disagree. Let them return structured findings, scores, citations, and uncertainty. Then route all of that through one merge point, always. After merge, exactly one writer node is allowed to mutate durable state. In my opinion, that rule is one of the cheapest reliability wins in agent orchestration. It is not mainly about avoiding a bottleneck. It is about shrinking the blast radius. If the system writes the wrong thing, the writer is the place to inspect, replay, pause, or roll back. Mechanically, build the graph in 4 steps. First, define reader nodes as read-only. They can fetch, parse, classify, and score, but not update shared state. Second, give every reader a structured output contract: source, claim, confidence, evidence, and proposed action. Third, collect those outputs at a fan-in node that deduplicates, checks conflicts, and produces a write plan. Fourth, acquire a lease for the writer before committing. The lease matters. If a run crashes and restarts, 2 copies must not publish the same decision. The writer should use item potency keys, write diffs, and log the decision it accepted, not every thought any reader had. Here is the shape from my daily builds. I run parallel fetchers that pull candidate changes, release notes, support signals, and test results. Then, scorers evaluate relevance and risk. Those nodes can be wrong, slow, or flaky without corrupting the ledger, because they only emit findings. The fan-in node groups findings by artifact, throws away duplicates, flags conflicts, and builds a publish plan. Then a single publisher obtains a writer lease and appends to the ledger. If the publisher dies halfway, the lease expires, and a replacement can resume using item potency keys. The readers gave me throughput. The one publisher gave me a blame trail. This pattern is not magic. It fails when a so-called reader has hidden side effects, like marking messages as seen, incrementing counters, or creating temporary records that other runs observe. It fails when the merge policy is vague and the writer has to invent decisions under pressure. It fails when the writer has no lease, so crashed runs can double write after retry. It also fails when the writer logs only success, not the diff, evidence, and reason. The trade-off is latency at the merge point. I accept that cost for durable writes. If you need more throughput, shard by key, but keep one writer per shard. In the graphs tier, this pattern sits between orchestration and state ownership. Earlier loop patterns ask, when do we stop, what do we verify, and what budget do we spend? Fan-out, fan-in asks, where is parallelism safe, and where must it collapse? It connects to budget control because N researchers can multiply cost quickly. It connects to verification because the merge point is the last cheap checkpoint before mutation. And it connects to guardrails because permission boundaries should match the graph. Readers get read scopes, the writer gets write scope, and the lease system decides who is allowed to hold it right now. Take one automation you already run and spend 10 minutes drawing its graph. Do not start with model prompts. Start with state changes. List every place the loop writes: files, database rows, tickets, comments, emails, cache entries, status flags. Now mark every node that could be read-only. If a node can do its job without mutation, remove its write permission. Next, draw one merge point before the remaining writes. Finally, add a writer lease and an idempotency key. You are looking for a sentence like this. Many nodes may propose a change, but only this node may commit it. 3 beats to keep. First, reading is safe to parallelize when the tools are truly read-only, so fan out your researchers, fetchers, and scorers. Second, writes need a merge point always. Parallel writers are race conditions wearing confident explanations. Third, exactly one node should hold the pen for a piece of durable state, protected by a lease and backed by an audit trail. That is not a bottleneck by default. It is failure isolation. New loop engineering episode daily on this channel. We are building the discipline of agent loops that finish, verify, and stop.